Welcome to our final lecture on the basics of hemodynamics. I know it's pretty dry stuff and there has been a lot of information to get through, a lot of it mathematically driven, but it just comes down to exposure. The more time you spend listening to these lectures, the more time you actually practice writing out the formulas, doing the equations, and asking about this stuff in your clinical placements, the more it'll start to make sense. Honestly, continuous exposure, you will actually get better at it. It will actually come all together for you. So the learning outcomes for this lecture, we want to identify how maximum pressure gradients have been used to determine the severity of stenotic valves. We'll explore problems when using maximum pressure gradients, their limitations and considerations. We'll learn the applications for the measurement of mean pressure gradients and how they may be used for measuring stenotic severity. And then the use of pressure gradients between the ventricle and atria to assess ventricular systolic function. The simple method uses maximum pressure gradient to assess stenotic severity. Basically, the higher the gradient, the greater the stenosis. Care has to be given, however, if there's anemia or polycythemia, outflow tract obstruction, significant regurgitation, or increased or decreased cardiac output states. These will significantly impact the obtained result, so it is good practice to not use this value in isolation alone when observing for stenosis. So if we're looking at the aortic valve here, if we obtained a peak velocity of less than 3.5 meters per second, most likely it's going to be in the mild category. Considering if we get velocities more than 4.5 meters per second, it's most likely to be severe. And then similar sort of numbers there associated for the pulmonary valve. Beyond limitations of the Bernoulli equation itself, there are also considerations when it's put into effect for the derivation of intracardiac pressures. Therefore, it is important to note that the pressures that are estimates only and that catheter-obtained measurements are considered the gold standard. An inaccurate velocity may be attained, such by improper setting of the scale or beam alignment that is not parallel with the flow. These can lead to an overestimation or underestimation of derived pressure gradients. If the calculation involves a subtraction of the velocity obtained, then an overestimation will occur. An inexpert sonographer may also interrogate the wrong flow. This is more problematic when the blind CW probe is in use. Aortic stenosis, mitral regurgitation, and tricuspid regurgitation all move in the same direction. Attention must be paid to the signal strength, the shape of the profile, and the duration of the flow that's obtained. As with previous hemodynamic calculations, beat-to-beat variability can play significant influence on the end result. Even in sinus rhythm, a number of measurements should be performed, not just a singular one. In the presence of arrhythmias, such as atrial fibrillation, bigeminy, and frequent ectopic beats, an average up to 8 beats is recommended. There is an increased probability of incorrectly estimating low pressures. We have discussed the application for pulmonary artery systolic pressure derivation. However, left atrial pressure may be estimated from the systolic pressure minus the gradient between the left ventricle and left atrium from mitral regurgitation. The values attained are large and the BP reading has error itself. Combining the two may easily lead to error of over or underestimation of the actual value. So we can see in our example here, we've measured a blood pressure of 130 over 85 millimeters of mercury, and our MR velocity is 3.5 meters per second. Plug it all into the calculation. So the BP systolic minus the 4V squared of the MR will get 18 milliliters of mercury. But if we incorrectly obtained a blood pressure of 135 and measured the velocity at only 5.2, a very minor error, we could see that there's actually a significant change there. Left atrial pressure now is determined to be 28 millimeters of mercury. The sonographer must also that a sphygma readings typically have an error of 5 millimeters of mercury either side of the actual blood pressure. This can be further increased with the selection of improper cuff size. Patients may exhibit Y-code effect where BP is significantly higher when they first enter, and the BP will change depending on whether the patient is sitting, lying, or in the left lateral decubitus position. It is also important to note that recordings to BP are also very rarely taken simultaneously with the Doppler recordings, so there is potential for fluctuations. We also need to be aware that right ventricular and left ventricular contractility isn't always simultaneous. This plays an effect when attaining a pulmonary artery systolic pressure from the pressure gradient this way. The right ventricle actually contracts slightly before that of the left ventricle typically, and also ends a little bit later than the left ventricle. Another method used to assess the mean pulmonary artery pressure is to evaluate the right ventricular acceleration time. This is obtained by placing pulse wave sample volume in the right ventricular outflow tract, extending out the sweep speed of the spectral display for ease of obtaining the duration, measuring the time from the onset of flow to the peak. This theory works around the principle that as pulmonary artery pressure increases, that the right ventricle must work harder against the high pressure to force the blood forward. Thus, as the work against the increased pressure, the acceleration time is shortened, or shorter periods indicate an increased pulmonary artery pressure. This is primarily true except for when significant pulmonary regurgitation exists. Normal forward flow plus the regurgitant flow moving through the pulmonary artery will have an artificially reduced slope period. Hyperdynamic or RV systolic dysfunction will also influence the slope itself. The mean pulmonary artery is also a useful indicator of pulmonary hypertension when the tricuspid regurgitation is not sufficient to determine the right ventricular systolic pressure. In catheter studies, it has been demonstrated that the peak pulmonary regurgitation velocity correlates well with the mean pulmonary artery pressure. The mean or average pulmonary artery pressure can be simply represented as 4V squared of pulmonary regurgitation. There are three methods that may be utilized for determining mean pulmonary artery pressure by the acceleration time method. There's the Mahan, the Kitabati, and the Bastian. In the final method, the pulse wave sample volume is placed in the proximal main pulmonary artery rather than the right ventricular outflow tract. It is therefore important to mention which method is actually employed when quoting the mean pulmonary artery pressure, whether it be from these here mentioned or the maximum pulmonary regurgitant velocity. The mean pressure gradient is also a useful value utilized in echo when it comes for the determination of stenotic lesions. This assesses all of the velocities over the duration of flow. The obtained mean or average velocity is the equation as we see here. 4 plus all the velocities under a curve squared divided by the number of lines that are actually taken. Typically, the machine will put in 100 samples or more. Unfortunately, the machine calculates this for us. There is a simplified gradient calculation that may be applied to native aortic valves with a maximum pressure gradient. Basically working, the mean pressure gradient is equal to the change in pressure divided by 1.5 plus 2. Simple changes around to our calculation, and the mean pressure gradient is equal to 2.4 the velocity squared. Here we have a set of typical mean gradients for the severity of stenosis for aortic, mitral, and tricuspid valves. So if we were to actually draw out what we do when we're measuring a mean pressure gradient, here's our baseline for the Doppler, and here's our flow profile. What we're doing is we're doing a tracing around the flow profile, as such, a little bit wobbly there. And then what the machine does for us is it puts in N, or 100 or so, different vertical lines from the baseline up to the point, and so on, all the way under the curve. And so what it's doing is measuring the average of all of these under the curve The summation of them divided by the number then allows us to actually have the mean gradient. And we could see here for the aortic valve, if we had a mean pressure gradient greater than 50 milliliters of mercury, that it indicates severe stenosis. Flow profiles may also be used to assess LV systolic function. The concept is known as dp/dt. D represents delta or change. Thus, it's the change in pressure generated over a change or period of time. Systole may be divided into two components, isovolemic contraction time and systolic ejection period. In the IVCT, the LV generates pressure with depolarization of the myocardium. At this point, force isn't sufficient to overcome the aortic pressure and force the blood out through the aortic valve. However, an incompetent mitral valve will begin to leak as soon as LV pressure starts to raise, that over the relatively low left atrial pressure. Hence, mitral regurgitation occurs in both periods and is often termed as a pansystolic murmur. We are interested in measuring the pressure change in the IVCT. The assumption is made that left atrial pressure doesn't increase during this period. Thus, we measure the instantaneous pressure gradient between the left ventricle and left atrium. Given the established relationship between velocity and pressure, we can apply that the rate of velocity increases represents a rate of pressure increase. What we expect to see is that in a normal left ventricle, function will generate pressure rapidly compared to an impaired left ventricle, which will generate the pressure slower. So continuous Doppler is placed with the best alignment to mitral regurgitation. Typically, this is applied to the apical four-chamber view, but we may need to actually reposition our probe to actually get alignment if the jet is actually eccentric. The sweep speed is specifically high because we're actually measuring a change over a short period, and so the greater we can draw out our sweep speed, the easier it actually is to measure these points. And then we take 2 points to actually measure the change in pressure. For simplicity and ease of use, we use the velocities of 1 meter per second and 3 meters per second. And then working with the modified Bernoulli equation of 4v squared, so 3 squared is 36, and 4 times 1 squared is 4, we're actually working out the pressure change between 36 minus 4, or 32 millimeters of mercury. So the dp/dt is simply 32 divided by the time taken. And then we have our set of values of what indicates normal LV systolic function. So a short period indicates that we've got normal systolic function, and an increased duration indicates severe dysfunction. Excuse the errors on the slide there. So we've described the principle as a change of pressure over a change of time. Thus, the measurements units for this are millimeters of mercury per second. So limitations and considerations of this method. Reduced left atrial compliance significantly affects the result that we obtain. Compliance, or the willingness of the receiving chamber to stretch, means that a small change in volume leads to a significant change in pressure. In acute mitral regurgitation, in flail, or vegetation with significant valve destruction, the left atrium does not have a chance to adapt to the sudden change or increase in volume. Thus, it is non-compliance, and the dp/dt will falsely give a result with numbers larger than expected. Significant afterload also affects the method of determining LV systolic function. In a patient that has aortic stenosis or marked hypertension, the LV must work against this afterload. As there is greater resistance to forward movement of blood, then the mitral regurgitation will deliver a signal which is sharper, with a slope steeper than expected, and thus we overestimate LV systolic function. An inadequate MR signal may lead to an underestimation of the DTB value or an overestimation of LV systolic function. This is typically apparent when there is eccentric mitral regurgitation jet, where it is difficult to obtain parallel alignment or place the cursor line at the origin of mitral regurgitation. Valve or chordate clicks may also make the determining of measurement points difficult. Mitral valve prolapse may also pose a challenge, as the valve is actually competent in the IVCT period. When the LV generates enough force to push the mitral valve back and cause the prolapse, then the regurgitation occurs. Often only a second half of Doppler profile can be imaged, and thus this technique cannot be applied. Now, this method may also be applied to assess tricuspid regurgitation for RV systolic function. However, obtaining the adequate TI signal can be challenging, and the technique is less well established with lower reproducibility. We can measure the time taken for pressure to change between 0 to 2 millimeters of mercury, or basically the time taken to generate a pressure of 16 millimeters of mercury. In summary, maximum pressure gradients may be used for more than just estimating pulmonary artery systolic pressure. There are other methods for determining pulmonary hypertension other than just tricuspid regurgitation, and these can be effective when the signal is not available. The mean pressure gradient plays an integral role for stenosis lesion severity. It correlates very well with catheter-derived measurements. And the DPDT method is a simple way of determining LV systolic function or RV systolic function, and is used along with other quantitative analysis forms.